Hi everyone. Today I will be talking about energy stored within capacitors and about how to charge them and discharge them and the analysis regarding that. Just a quick reminder, we said capacitors separate charges by and in that way they store energy. So in this case we're going to analyze how much energy is stored by capacitors when they're fully charged and how to calculate that as well. But the idea is that since we have charge being separated across the capacitor due to the insulator in the middle, there is energy stored. There is potential. So if I had my capacitor connected to a cell, so this is a cell. I've got my capacitor. I'll just be careful not to make the lines the same, a bit different lengths. They have to be the same length. So if I charge this capacitor here fully, so then it will have, let's say if this was 6 volts, now that will be 6 volts. Once I disconnect it from the cell, so all the energy is stored across the capacitor, and I connect it to so this is the capacitor still, the same capacitor that we were talking there. If I connect this charged capacitor to a light bulb, what you will experience, so while we spoke about how it's charging, how the electrons build up on one side and how the electrons move away from the other side, so you have an overall positive charge. In this case, so if this was the positive and negative terminal of that side, in this case what you will experience straight away is the electrons flowing around straight away as soon as you connect it to the light bulb. And remember, we need energy for anything to happen anywhere anyway. So, too many any's. So the idea is that the energy stored by the capacitor is now being transferred electrically to the light bulb, and then the light bulb uses that energy to emit light waves, and also in the form of heat, so mostly infrared radiation. So we have the electrons that have built up on one of the plates of the capacitor. As soon as you connect it to the light bulb, you're giving them a route to flow through. So what you experience is also these electrons with all that, with each carrying an individual amount of energy, going to the light bulb, dropping that energy and returning back. So you have that flow of electrons that carry energy, and you have the light bulb getting lit up. So what about energy now? There's two important factors that relate to how much energy a capacitor can store. And that the first factor is the actual capacitance of the capacitor. The second factor is the starting or initial potential difference. So the energy stored by capacitor depends on the capacitance. Remember, capacitance is quite similar to what resistance is. So we have different resistors that have fixed resistors that have fixed values of resistance. So you have a 5 ohm resistor, you can have a 10 ohm, 100 ohm, but you don't have 133.3 ohm. And so on. The same thing with capacitors. They have their capacitance, their ability to store charge per unit potential difference. We already defined that. So it is a property of a specific capacitor depending on how it was built. So the amount of energy stored depends on how much charge per unit voltage you can store and the starting potential difference across the capacitor. So let's just focus a bit more now on where does that energy stored in the capacitor comes from. So we already know that this is the negative, positive part of a cell, and the electron. And just to remind you, we only are interested in the electron flow when we're discussing what's taking place with the electrons and how they accumulate on one side of the capacitor. So when we talk about capacitors and how they charge, we focus on the electron flow. Otherwise, everything else that we've done in electricity prior to this, we always cared about conventional current, which is opposite a direction. It's not a real flow of ions charged particles moving, but we had to stick to it, and you'll find out more in the next chapter of why. So let's start with explaining what is going on with the electrons. So what we have, let's say this capacitor is still getting charged. Now this happens very quickly, but we're assuming that it's not happening very quickly. So we have the electrons flowing around, some of them already accumulated on this side, but it's not fully charged yet, so there's more electrons coming towards it. So let's focus on this electron right here. Now this electron will be approaching the already negatively charged plate because already some charge has accumulated on it. Now obviously negative and negative repel, just like the north and north side of a magnet or the south and south side of a magnet. And what the battery's job, or the cell's job to do here is to push the electron towards the plate. In order for that to happen, you need to have an external push for it to build up on the actual plate. But this is where the external work is given by the battery or power supply or a cell that you have connected to it. So all the energy stored in the capacitor comes from the energy of the battery, cell, or power supply. Also, a good thing to mention here is that obviously we have electrons on this side as well. Let me just keep the same color. So we have electrons on this side, and the electron is attracted by the positive charge, but it has to be pulled away. So this electron here is actually attracted to them, but energy is needed for it to be external work done, needs to be done to push it away. When we talk about work done, remember, it's the same thing as energy transfer. So if I use the words interchangeably, then please remember that work done is the same thing as energy transferred. So that's how that's where the energy stored in the capacitor comes from the energy of the battery or the power supply. And you will consider this as well before I move on to the next part. When you have a north and north of magnets, of two separate normal magnets, and you place them near each other, you will constantly experience a push away from each other. So when we talk about external work done or external energy, is you pushing them closer together. So this is going to be your external energy being inputted into the magnets to get closer together. As soon as you let them go, obviously, they will push each other as far as possible as they can, depending on what strength they have. So you look at it in that way. If you have to push two magnets together that are repelling, then you are inputting your own energy. That's external work done on the magnets. The same thing takes place here. So now we'll move on to the first learning outcomes. Obviously, even though this is not part of the learning outcome, it is hinted that you should know about it. So let's go back to the first things that we learned about capacitors. So what is capacitance? We said capacitance is the charge stored per unit potential difference. Let me just use black, might be better. Now, if I look at this equation, Q is equal to CV for a specific capacitor, C is constant. So if I consider also the equation of a straight line, Y is equal to mx plus C, and I plot a graph of, for example, V against Q, so we'll have V. So potential difference against charge. Obviously, I need to rearrange my equation to match it because now I labeled my y-axis to be V. So that would be V is equal to 1 over CQ. I'm just simply rearranging this equation to match my y-axis variable with y and to match my x-axis variable with the quantity I have there. So it will be V is equal to Q over C actually. which is the same thing as this here. So what we have, our y-axis is our potential difference, our x-axis is charge, and our gradient will be 1 over capacitance. Always use this format, always rearrange your equation to match your y by itself. Just leave your y variable, so the one that you plot on your y-axis, rearrange and make it. So in this case, our y-axis is v, so I simply rearranged, made this the subject of the formula, and brought over c. So always make sure that whatever's on your y-axis stays on its own, and everything else works out from there. So we have this, and obviously I know that this doesn't have a y-intercept, so that means my line starts exactly at the origin. You are expected to state things like that in exam questions. They will ask you, what would you expect the graph to be, or your results, how would you analyze them, and so on. So you need to make sure that you always state, even if it's obvious, you have to state it, otherwise you don't get marks for it. And since it matches the equation of a straight line, then it's also a straight line going through the origin. So that's your graph for V, potential difference against charge. What does this have to do with energy? Well, here we need to go back to a bit of our previous knowledge of electricity. We learned, and that's one of the equations I told you, to make sure you're always feeling confident, because a lot of people actually don't know how to apply it, even though the equation is given to them. Is the definition of potential difference, which is linked to energy transferred or work done and charge. So the most common ones is current is charge divided by time, and the potential difference is work done per unit charge. These are the main ones. Many people are okay with this one. Not many people are okay using this one. Remember, this is work done or energy transferred. It's the same thing. This is charge, and this is potential difference. So what we have here is an equation for calculating how much energy could be potentially stored within a capacitor. However, our graph, going back to the graph I just drew there, it's a straight line going through the origin. And if I am to get the area, and as you can see, as more and more charge is getting stored, the potential difference increases the same rate as charge is being stored. So if we look at the graph, no other devices behave quite like capacitors. So the graph will be different from what we would expect from anything else. Usually it will be a straight line, a straight flat line like this for the components. But this is not the point right now. So we'll focus on capacitors. Now we know that energy transferred from the equation that we learned in the electricity topic, work done or energy transfer is equal to the charge times the voltage. In this case, it will be the area under this graph, because it's the voltage, this is the voltage times the charge stored, but also this is a 90-degree triangle. So my work done for a capacitor, remember this is for other electrical components. But for my capacitor, this comes out as a triangle. So my energy transferred is height times base divided by 2. Don't forget your basic maths in terms of area of triangles and so on. So what we have is work done is a half VQ. Once again, work done or energy being transferred is W. V is potential difference. Remember, this is measured in joules. This is measured in volts, and charge is measured in coulombs. So Q is charge. Don't forget this. So not only are you actually calculating the work done on the charges, but you're also calculating the energy stored in the capacitor. It's exactly the same thing, because the work done, the external work done on the charges by the cell or battery is the exact same amount of energy stored within the capacitor. Just wanted us to quickly jump back and see what the learning objectives are expected from the specification. So we talked about how the energy stored is the area under the graph. And then it says energy stored by capacitor can be calculated, obviously, using these three equations. We proved this one, and you should be able to prove it too. And now we're going to have a look at how we can get to these two. It's quite simple. It's actually one of the easiest proofs that you can have. And it always starts with this equation and the capacitance equation. So you have Q, you have C is equal to Q over V, and you have the work done is a half QV. Now, if you don't know, for example, the voltage and you know the capacitance, or you don't know the charge and you know the voltage and capacitance instead, there's different equations that you can use for it. So let's start with the first one. You can see that in this equation, you don't have voltage. That means I can use this equation, rearrange it, and get rid of the volt and substitute in there to get rid of the voltage. So V will be Q over C. Once again, I'm simply rearranging this to make V the subject, so I can substitute it in there and get rid of the V as a letter present in my equation overall. So that will be work done is equal to a half Q times V, which I rearranged here, just Q over C. That's a half Q squared over C. And then I have the other equation, which clearly shows that you have a V but not a Q. So I will rearrange and a C as well, which is obviously included in this equation. So I will rearrange to make Q the subject of the formula this time, where Q is equal to CV. And I will substitute it here instead and leave V alone. So work done is equal to a half CV times V. And I end up with a half CV squared, or V squared C, whichever way you like, it doesn't matter. So that's the second point crossed off. And this will be a good point to start talking about some uses of capacitors as storage of energy. So a lot of your mobile phones, maybe not every single one, because they do use different types of technologies, but most of your mobile phones do use capacitors in the screen as sensors. So when you press your thumb on the screen, you're temporarily storing a bit of energy at the part of the screen. That's why you get reaction, and that is being released and it's being changed into information in your phones to do the action that you have done, so to complete the action. Now, when it comes to your flash, for example, your camera flash, that's also due to capacitors. So what happens there is that you have energy stored in the capacitor, and when you take a picture, all that energy is being released at a very, very small amount of time. So capacitors can store small amounts of energy, but since they release that energy very, very quickly, it actually generates a high output power. So I'll give you an example. Let's say you have managed to store 1 joule of energy. So your energy is your capacitor stored 1 joule of energy. Now, when if you release that energy in a flash in a fraction of a second, so 1 millisecond, then the power output that you have is much bigger if it was 1 second. I'll show that. So power is the rate at which energy is being transferred. So work done divided by time. That means that you have 1 joule divided by 0.001. That gives you 1,000 watts or a kilowatt. Now, if you had the same amount of energy being transferred in 1 second, that will mean that your power is 1 divided by 1, which is 1 watt. So it doesn't necessarily mean that even though capacitors cannot store huge amounts of energy, unless you talk about supercapacitors, and that's something different, that I can put a bit of extra reading for you if you want on that. But if, for example, capacitors, even though they don't store a lot of energy, they actually do have high output power because they release the energy quite quickly. And when we do experiments, you will also see how the light, when we connect it to an LED, for example, how the LED only blinks, the light of the LED only lasts for a fraction of a second. So quick, not a fraction of a second, but a couple of seconds, depending on how much charge we manage to store in the capacitor. Other uses of capacitors are, for example, I said TV, camera flash. They also use specific capacitors in some labs to provide high amounts of power. For example, accelerators, the particle accelerators, and they can be used for backup power when, for example, emergency lighting, or for computers if something happens wrongly with the power supply. So this is an example before I move on to the harder parts of this chapter. They're not that hard once you get used to it, but it's a bit different. So this is an example question. It says two 300 microfarad capacitors are connected in series to a 24-volt power supply. I always tell you, when you look at circuits, you always draw the diagram quickly so you can label it, so you can play with it a little bit if you need to, and to keep your thoughts in one spot. So you have two capacitors, they're both 300 microfarads. So just labeling my values, keeping everything in the same place, and a 24-volt power supply. I need to calculate the energy stored, so work down the W letter. But we only spoke about specific capacitors storing specific energy. Remember, when we have two capacitors in series or in parallel, we need to get their total capacitance. And unlike resistors, when they're in series that add up their total resistance, capacitors have a smaller capacitance when you combine them together. So remember, the equation to use is this one. You should be able to prove it. It's in my previous video if you haven't done so already. Or you can simply put this in your calculator as this. Now you have CT is 300, and then you'll end up with 150 microfarads of total capacitance. So that's my total capacitance. I have my total volt potential difference stored as well. So that means I have V and C. Now we saw three different equations. We saw this for the energy stored in a capacitor. I don't have Q and I can't be bothered to calculate separately. So that means I can use another equation. We have seen a half V squared C. Now this looks good because I have C, I have V. That means I can calculate that as well. So that gives me a half 24 squared times the capacitance. Now remember, capacitance in this case is in microfarads. So you do need to convert that into farads. And that will give me about 4.3 times 10 to the minus 2 joules. So you can see these two capacitors actually don't even store that much energy. They store 0.043 joules. That's a very tiny amount of energy. So we have seen so far how to calculate capacitance of a capacitor. We know charge and voltage. We've seen how to calculate the energy. But we haven't spoken about yet about how these values like charge, current, voltage in a circuit vary with time as we're charging and discharging the capacitor. So all the equations we have seen link different variables together, but none of them consider how charge builds with time. So for example, in this diagram here, I talked about how you have the electrons moving until it's fully charged to 6 volts and there's no movement no more. But then we also need to know how much charge or energy is stored. Let's say if it took it 10 seconds to fully charge, I should be able to calculate how much energy it would charge up to after 5 seconds or after 2 seconds or 1.5 seconds and so on. And this is a relationship we're going to see now. And this is where it will get a little bit more complicated before it gets easy again. So I will be introducing exponential decay, and I will be introducing natural logarithms and how to deal with them.